The concept of limit of a function is one of the fundamental ideas that distinguishes calculus from algebra and trigonometry. In this chapter, we will discuss the definition of limit to estimate limits, to determine whether limits of function exist, use properties of limits, and direct substitution to evaluate limits. First, I will define limit. Suppose f is a real valued function and a is a real number. Then the expression limit extends to a fx equal to L means that by making x sufficiently close to a, fx can be made close to L. In that case, the above expression can be read as the limit of fx as x approaches to a is L. But that was the informal definition. We have to be more precise. Suppose fx be a function and a be a real number, then limit extends to a fx equal to L means that for any epsilon greater than 0, we can find a delta greater than 0 such that if x lies between a minus delta to a plus delta, then fx will lie between L minus epsilon to L plus epsilon. Graphically, this means that the part of the graph that lies in the blue vertical strip will also lie in the green horizontal strip. To illustrate this, consider the function fx equal to 3x. We want to find the limit of fx at x equal to 2. First, construct the table of x and corresponding fx. For x equal to 1.9, we get fx equal to 5.7. For x equal to 1.95, we get fx equal to 5.85. In a similar manner, for different values of x, we get different values of fx. Here we observe that the limit of fx as x approaches to 2 is 6. This can be observed from the graph also. Note that there are essentially two ways x could approach to a number a, either from left or from right. This naturally leads to two limits, the right hand limit and the left hand limit. If x approaches to a from left, then the limit is called left hand limit and is denoted by limit extends to a minus fx. If x approaches to a from right, then the limit is called right hand limit and it is denoted by limit extends to a plus fx. If limit extends to a minus fx equal to L and limit extends to a plus fx equal to L also, then we say that limit extends to a fx equal to L. To illustrate left hand limit and right hand limit, consider an example. Suppose fx equal to x plus 2 when x not equal to 1 and 0 when x equal to 1. First, construct the table of x and corresponding fx. For x equal to 0.9, we get fx equal to 2.9. For x equal to 0.99, we get fx equal to 2.99. In a similar manner, for different values of x, we get different values of fx. Here we can observe that limit extends to a minus fx equal to 3. Also, limit extends to 1 plus fx equal to 3. Since the left and right hand limit both coincide, we have limit extends to a plus limit extends to 1 fx equal to 3. This can be observed from the graph also. Consider another example. Suppose fx equal to 1 when x less equal to 0 and 2 when x greater than 0. From the figure, it is obvious that the limit extends to 0 plus fx equal to 2, that is the right hand limit of fx is 2 and the left hand limit of fx is 1. Since the left hand limit and right hand limit are not equal, the limit of fx as x approaches to 0, that is limit extends to 0 fx, does not exist. Next, I will state some properties of limits. Suppose fx and gx be two functions and limit extends to c fx equal to L and limit extends to c gx equal to k. Then property 1, scalar multiple. Then limit extends to c b into fx equal to b into L. Property 2, sum or difference. Limit extends to c fx plus minus gx equal to L plus minus k. Property 3, product. Limit extends to c fx into gx equal to L into k. Property 4, quotient. Limit extends to c fx by gx equal to L by k, where k must not equal to 0. Property 5, limit extends to c fx to the power n equal to L to the power n. To evaluate limits, first consider the limits of polynomial and rational functions. If p be a polynomial function and c be a real number, then limit extends to c px equal to p of c. If r is a rational function such that rx equal to px by qx, where qc not equal to 0, then limit extends to c rx equal to pc by qc. To illustrate this, consider the examples. Example 1, limit extends to 1 x cube plus x square plus 2. Since this is a polynomial of degree 3, we can put the value of x. So, we get 1 cube plus 1 square plus 2 equal to 4. Example 2, limit extends to 2 x square plus 5 by x minus 1. This is a rational function, and also if we put x equal to 2 in the denominator, this is non-zero. So, substituting this, we get 2 square plus 5 by 2 minus 1, that is 9. But if this rational function is of the form 0 0, we try to rewrite the function cancelling the factors. For example, we choose limit extends to 2 x square minus 4 by x square minus 2x. Here, if we put the value of x equal to 2, then we get 2 square minus 4 divided by 2 square minus 4, that is 0 by 0. So, we can rewrite it as limit extends to 2 x minus 2 into x plus 2 by x into x minus 2. So, x minus 2 get cancelled. So, we get limit extends to 2 x plus 2 by x. So, again this is a rational function. So, again we will put the value of x equal to 2. Then we get 2 plus 2 by 2, that is 4 by 2. Since this is not a 0 by 0 form and we get a finite number, so the answer is 2. Here some important limits. Limit extends to a x to the power n by x minus a equal to n into a to the power n minus 1. Limit extends to 0 sin x by x equal to limit extends to 0 tan x by x equal to 1. Limit extends to 0 e to the power x minus 1 by x equal to log e base a. In particular, if a equal to e, we get limit extends to 0 e to the power x minus 1 by x equal to 1. Then limit extends to 0 log 1 plus x by x equal to 1. Limit extends to 0 1 plus x whole to the power 1 by x equal to e. These are some important limits.